Okay, let's have a look, see what we can get, and slowly go that way, and then you guys can do the question yourself later, okay? Let me grab different color pen. All right, so the first thing I do is I'm going to look at this object. Because this object, I know the acceleration. Because the acceleration give me, basically tell me there's a net force, and then I can do force analysis on it, right? All right, let's have a look. What are the forces acting on this object over here? Gravity, yeah, going downwards, and what else? Tension. And there's a tension force pulling upwards. So which one is bigger?
Gravity.
Yeah, obviously gravity is going to be bigger because it's accelerating downwards, right? Okay, through this, I can actually just calculate how big this tension force is going to be. Does that make sense? Mm-hmm. Okay, sweet. Let's have a try. So gravity, I'm going to start with, gravity is going to equal to mg. That equals to 25 times 9.81. I'm just going to use 10 to make the numbers easier, okay? Because we're not focusing on calculation here. We're trying to focusing on the theory. So that gave me 250 Newton, right? Okay, have a think. What is the next step? Next step, we're going to try to figure out the tension force, right? So in order to figure the tension force, we need to know the acceleration. Yeah, we know the acceleration. We need to know the net force first, right? Okay, let's say this. So the net force gonna equal to ma, which equals to 25 times 2.0, give me 50 Newton. Right? Okay, and where does this net force come from? Yeah, net force is the gravity is bigger, so it's gravity minus the tension force. So net force is 50 equal to gravity, 250 minus Ft. So now I know tension force equal to how much? 200. Okay, so far I'm using level 2 physics, right? Make sense? Okay, so now I'll write down, okay, this equals to 200 Newton now. Okay, and then I'm going to keep going around. Well, if there is 200 Newton pulling it upward, how much force is pulling downwards? Is it 250 or is it 200?
250.
There is a force pulling here at 250. And then how much force is going to be experienced going over here, going downwards?
50 units.
What is this?
50? No.
Negative 50.
No. This force will equals to 200 Newton. The reason why is because tension force always come in pairs, and they are gonna be same size and opposite direction. Say this, if I have this thing, I'm pulling this thing. If I'm pulling 200 this way, how much gonna go this way? 200 as well. Tension force always come in a pair, and they'll always be the same size. Does it make sense? You cannot pull your hair 200 Newton that way and only give 50 Newton this way. Does it make sense? I wish I have a long hair so that I can pull it, you can see it. So the force has to be the same size. So let's have a look. Even though you got 250 pulling over here, how much has been used to make this thing accelerate? 50 has been used to make this thing accelerate. And then the 200 is pulling downwards, which gives you the 200 pulling upward. So that's why the tension force over here is going to be 200. How many of you guys think that makes sense? Raise your hand.
Doesn't it cancel out
What cancels out?
the tension force?
No, that does not cancel out because this 200 is pulling down on this part,
Yeah.
and this 200 is pulling on this object going up. So they're not working on the same object. So this is like the action force and reaction force. If I push 200, it will give me 200. They don't cancel out because they're working on the different objects. So basically, this is actually Newton's third law of motion. Okay, yes. Oh no, just touching the glasses. Okay, so now, I know the tension force. Then what can I link to this rotational system? What can I find? Yeah, we can find the torque, right? If we have a tension force pulling here, that's going to give this thing a torque. Yes?
How is there inertia? It hasn't started moving. It like starts moving and stops, isn't it?
It's going to start accelerate. This thing is accelerating down. If this thing accelerates down, what happens to this thing?
It'll go up.
It's going to accelerate upwards, right?
But how is there inertia if they're not moving?
I'm not
What's the
talking.
otherwise
Oh, inertia is a property of matter. It doesn't matter if it's moving or not. You always have inertia. The inertia, rotational inertia, it don't want to rotate. It doesn't want to rotate. If it's rotating, it doesn't want to stop. It just want to keep rotating. So that is rotational inertia.
So
Yeah.
is the torque only provided by the tension force and not the unbalanced force? Like the
Torque can be provided by any force. But if you have two forces acting, one is going to have a clockwise torque, one is going to have an anti-clockwise torque. If we look at this object, it's going to rotate, right? Why does it rotate? And that's because there is a tension force here making it going anti-clockwise, have a torque. And in this one, we have a force going downwards, trying to make it going clockwise. But which torque is bigger? Yeah, this one is going to be bigger. That's why it's going to go anti-clockwise.
So why wouldn't we use FG to find torque?
And that's because FG is not acting here. If we analyze here, we've analyzed this situation. If we look over here, what is making this thing going down?
Okay, yeah.
It's very important. Say this. If I draw another situation. Say gravity here is 100 Newton. And then over here I have a 1 meter distance. I say torque equal to F times R, which equals 100 times 1 equal to 100 Newton meter. Is this correct?
No.
There's a gravity that is 100 Newton pulling this object downwards, and then there is a distance 1 meter. Can I just say the torque this thing experiences is going to be the 100 Newton times the distance, give me 100 Newton meter? No, it's wrong. Why? Because this gravity is not making it going down. Rather, the tension force here making it going down. There will be, say, 80 Newton tension force, right? And then there's a 80 Newton tension force going up. So the 100 Newton force, 20 of it has been used to make this object accelerate downward. And then only 80 Newton is going to be passed on to here to make it rotate. Does it make sense? So you cannot use this just to find that. But if you have this situation, if I tell you this is the 100 Newton pulling downward, well, that 100 Newton is completely pulling it downward. But if I say it's the gravity, or the object's gravity, well, the object could be accelerating. So the pulling force is actually not going to be that big. Does it make sense?
Wait, sorry, can you repeat the last part?
I say if it's a gravity over here, not all of its gravity is going to be used to pull this thing down. Some of it is going to make the object accelerate. Once it accelerates, the tension force is actually going to become small. Does it make sense? And the tension force could be bigger than gravity as well. If the object is rotating the other way, then it could be bigger as well. Does it make sense? Say this, if I'm holding a string like this. Right now, this object has a gravity going down, right? And right now, the gravity is going to equal to my hand's pulling force, right? So that's the tension force. If it's dropping, and how big is the tension force here? If it's dropping completely, actually have zero tension force. Does it make sense? or if it's dropping a little bit slower, then it will be smaller than my actual gravity. So the tension force is going to be small. So I don't need 100 Newton hold this thing. Actually, I only need 80 Newton because it's falling. Does it make sense? So that is the reason why we have to train ourselves, like not to think, oh, 100 Newton is pulling that. Rather, 250 Newton is pulling, but at the end, when it comes to here, there's only 200 Newton force now. Does it make sense? Yeah.
So will it always FT be smaller?
No, not necessarily. We're going to look at this one, then we'll see FT is actually going to be bigger because this object is going to accelerate back upwards. If it's accelerating down, the T will be smaller than gravity,
Okay.
depending on what direction it's accelerating.
So
Yeah.
as the object falls down, the tension force would decrease to become less than gravity. So would the you know how there's two pairs of tension force?
Yeah.
Would the other pair also decrease?
Yeah, these two pairs always have to equal each other.
Yeah. So then the torque would decrease.
Yeah, torque will decrease, yeah. Okay, so right now, the tension force is going to be 200 Newton. Can we establish that?
Yeah.
Yeah, that is because this tension force is going to be 200 Newton. We calculate from this object over here, right? Tension force equal to that. Okay, so now let's have a look, see how much torque does it provide this object over here. Okay, let's say this. Number 3 is, this is clockwise torque, right? Or this is anti-clockwise. So the anti-clockwise torque is going to equal to the tension force multiplies the radius r. So it's going to equal to 200 and times 0.5 equals to 100 Newton meter. Does that make sense? Okay, so here comes something tricky. The hard thing, we cannot use this torque because you know how torque equals I alpha, right? Jen, do you have your notes? You didn't even write anything down. This torque is not going to be used to make this thing accelerate. Why is that?
Because there's
Yeah.
torque.
Because there's another torque going backwards, right? So we cannot use this divided by this to get the acceleration. So this thing is gonna, because there's another one over here, right? So, well, how do we find the angular acceleration of this thing?
The acceleration divided by.
Yeah, very good. Now, number 4, I can find the acceleration of this thing because I know the linear acceleration over here is 2 meters per second. So linear acceleration is going to equal to rotational acceleration times r. And this r is going to be my capital R. Does it make sense? Because if this thing is accelerating downward, it's going to make this rotating thing accelerate. Right? So now I can write over here, okay, my acceleration is 2.0, that will equal to alpha and times the radius, which is 0.5. So now the alpha is going to equal to 2.0 divided by 0.5, so that becomes 4 rad per second squared. Does that make sense? Okay, so I just quickly move my camera to over here. Can I see the whole board? Oh, I moved take the computer away. I just want to shoot this part because later if you find like struggling, then you can have another look, okay? All right, so now I know the alpha, right? Acceleration now. Well, what makes this whole thing accelerate? Not this torque. Rather, there's a net torque that makes it rotate, right? Okay, so now, step 5, I can know the net torque is going to equal to alpha times the inertia. Inertia is 4, alpha is 4 as well. That gives me 16 Newton meter, which is my net torque.
Wait, so is that torque for the smaller one?
No, that's not the small one, that's a net torque.
The whole
that's
system.
all. So then the other one was for the.
Very good, yeah. So now, once we know the net torque, we can find the torque of this tension force over here. Does that make sense? Okay, so number 6, the net torque equal to the anti-clockwise minus the clockwise torque. So 16 equals to the anti-clockwise 100 minus clockwise. So now we know clockwise is going to equal to 100 minus 16. That gives me 84 Newton meter. Does that make sense?
But wasn't the last one the net torque?
This one?
No, the last one.
This one is the net torque.
Oh, right.
Yeah, that's the net torque. And from the net torque, then I can find the clockwise torque. Okay, and then from this clockwise torque, what would I be able to find? What does this clockwise torque come from?
The B.
Yeah, now I can find not the weight of the B, rather than we can find the tension force, because that tension force gives you the torque. I call it Ft dash because it's another tension force. Okay, and then I'll write over here that number 7, that clockwise torque comes from the Ft dash times the little r. So now the Ft dash is going to equals to 84 divided by 0.25. So that will give me what? $336 Newton. Does that make sense? Because that torque is coming from this tension force, right? Okay, so then I know, well, this force, I know it's going to be 336 Newton now. Does it make sense? Yeah, okay. Is this going to be the gravity?
No.
No, it's not the gravity. And this is the tension force going down. So now we want to know the mass of this one. Now we've got the tension force over here. What would this tension force be? 336 Newton. Okay. So we want to find the weight of this one. If we can know the acceleration, we will be able to find the gravity force over here. Does it make sense? Okay, how do we get the acceleration of this object B?
Angular multiplier.
Yeah, and then I can use that equation again. The acceleration of this second object is going to equal to alpha r again. Does that make sense?
Is the angular acceleration for both objects equal?
Equal. Angular acceleration, there's no two objects. There's only one angular
Like
acceleration.
one system.
Yeah, it's one system. Yeah.
You know how the 25 kg is going down at 2 meters?
Yeah.
The acceleration is 2. Why isn't it going up at 2?
This is not going to happen because the radius is different.
But isn't it in the same system?
No.
It's in the same rotational, yes, it's the same. But linear will be different. Because this one is having a big radius. So if it's moving a lot over here, here only move a little bit. Say over here you move half of a circle. That's this much distance. Right? But this one you move half a circle, only this much distance. So this one will be a lot smaller than this one, acceleration. Does that make sense? That's why this and this one, the rotational is the same. So I can use this, get the rotational, and from the rotational I can get the acceleration of this one. This is what we call pulley system, right? So you pull over here, and this thing is going to go up. You have to pull a lot over here for this to go up a little bit. Yeah? Because as toilet paper is running out, for the same rotational, you only come out a little bit of toilet paper. Does that make sense? So that's why even you keep the rotating the same, but the radius has decreased, then there will be less distance coming out. Okay, so now using this one, now we can calculate, well, alpha is how much? Over here, 4. Now I need to times 0.25. So the acceleration of this one is going to be 1 meter per second squared.
Oh, so you can use this one alpha.
Yes, so right.
Yeah, because alpha is the same, because it's the whole system is the
It's like
same.
the whole system. Because it's not linear, it's angular, so it creates the whole.
Does that make sense? Okay, and then once I know that is 1 meter per second, and then I will be able to use the same analysis that it gives me the mass of this one. Okay, so how do I do that? I write the last step. So the net force of that one now is going to be the gravity going down. Which force is bigger?
Tension force.
Tension force. So now it's going to be Ft dash minus the gravity force, and that will give me ma. Because now tension force is bigger now, right? Okay, and then I put the thing here n. How big is tension force? 336, right? So minus m times 10 equals to m times 1. Give this a dash. And then I go 11 mass equals to 336. So the mass, now I'm gonna give it a dash as well because now this is a new mass, a smaller mass, mass B. That will equal to 336 divided by 1 equals to 10.6 kg.
Mr. Wong.
I think it's 30.5.
Oh,
Yeah.
I was so confident. I was like, look at this. Is that right? What is it?
Yeah, 30.5.
Oh, 30.5. 30.55.
Oh, yeah.
Okay, 30.6.
No, No, it's 30,
no, it's
no,
5.4.
30.54, but if
Oh,
you run
okay.
it down.
And then 546. 545.
No,
545, 545, 545. Oh.
Where does 11m actually come from? What is the number of it?
That's here. Minus 10m equals to 1m.
He just said that we only have 21 because it's
Does it make sense? This is a scholarship question. If they ask you that, I mean, look at how many steps they have. So in your exam, what they're gonna do is they might make a half of it, that will be achieved, then give you a merit, and then give you excellence. Or like they might say, well, that is merit, or that's excellence, this is achieved merit, that's merit. They might break it down to a few questions. But if you know how to do all of this from the beginning going to the end, now you will solve all problems like this.
Can you just explain where you get to 11m from?
Okay, so that is 336 minus 10m dash equals to 1m dash.
Yeah.
Then move to that side.
Minus
Yeah.
Ah.
11m, okay.
Yeah.
So also if you return it to that.
Yeah.
All good?
So what is this mass? We have mass.
Okay, so